In the previous segment, we had a look at the two most simplest versions of quantum mechanics, namely for a point particle and for a two-level system. Now we're going to have a look at how we can take these systems and compose them into more complex ones. For a point particle, this is actually already built in some ways when we move from 1 to 2 or 3 dimensions. So let me briefly describe what I mean by this, because this prepares us nicely for what we are going to do next. If you think about the wave function of a particle in 3 dimensions, then you write it, for instance, in Cartesian coordinates as a function of the 3 different coordinates. But nothing tells you that this is actually not 3 different coordinates of 3 different one-dimensional systems. So this could also be interpreted as a wave function of 3 particles moving in 1 dimension with coordinates x1, x2, and x3. Indeed, everything which I told you about the point particle before in 3 dimensions would simply apply to this situation of 3 particles, assuming that these 3 particles are so-called distinguishable particles. So they have very specified labels, 1, 2, and 3. And even though these might be fundamental particles, we would have to assume that we can distinguish them in some ways. For instance, they might be fundamental particles of a different type. So this could not be 3 different electrons, for instance, because then there are additional constraints on the wave function derived from the Pauli exclusion principle. So the wave function would have to be asymmetric in that case. This is because there would be fermions. And if you would do the same for 3 photons in 1 dimension, then the wave function would have to be symmetric. Photons are also indistinguishable particles, but they are bosons. But if we look at distinguishable particles, then we can think about this wave function simply as a function that describes 3 particles at the same time, distinguishable particles. And so, for instance, we would have 3 position operators, x1, x2, and x3. And these are just associated through these coordinates, and we would have 3 momentum operators, just taking derivatives with respect to these 3 different positions of these particles. And now you see that these particles act actually quite independently of each other. For instance, the momentum of one particle is a simultaneous observable with the position of another particle. So the commutator between, say, x1 and p2 would now vanish. And of course, you could just extend this to a larger collection of particles. Nothing prevents you to stop at 3, and you can make the system as complicated as you want. So we actually already have everything in this context, because we could already write down the complete quantum mechanics for, say, a particle in 3 dimensions, and we would simply apply the very same rules, just with this different interpretation, to these 3 particles or even more particles. So that's really all that I wanted to say about this point, because in this course we are really interested in the 2-level systems. So let us generalize this to arbitrary composed systems, and then we can specify this later in the next step again to 2-level systems. The key feature that helps us with this generalization is the observation that the wave function depends on all the degrees of freedom of the different particles, and indeed covers all possible combinations of these degrees of freedoms, in this case the positions of the particles. So let us start with the states of a composed system. Let us say that our composed systems have discrete states that we can either label by n or by m. So these are labels for 2 different distinguishable parts of a quantum system, and we want to describe the complete system here. Let us assume that the index n is running from 1 to capital N, and so this is the index of certain basis states n, say an orthonormal basis. And similarly, we have this index m for the second part of our quantum system, and this is running until capital M, and again this enumerates states for this part of the quantum system. Now the quantum states of these 2 different parts of the systems could then simply be written in the most general way as follows. So what we have here is that we have wave functions for each of the two systems, and these indices cover all the individual possible states of these systems. Now when we want to write a wave function for the composed system, in analogy what we said for the three particles, we need a wave function that covers all the possible combinations of these degrees of freedom. So this would be a wave function which covers all the possible combinations of these degrees of freedom n, m, n in terms of amplitudes. And these we have to interpret in terms of basis states, which now simply enumerate the joint states of the quantum system. So this is a basis state in which system 1 is in state n and system 2 is in state m. So these two different parts are just in these individual states. And then according to the superposition principle, we need to allow for all possible combinations with arbitrary amplitudes in front of this. Now this looks a little bit like a matrix, but it is not a matrix, it is still a vector. And there is a very simple way to think of this. Just think about these as different digits in a number, and we are just going to enumerate this number. So that would be if n and m would be running from 0 to 9, for instance, covering all the numbers from 0 to 99. And indeed we are going to collect all these entries in a vector exactly in this way. So we are going to start out with the entry 1, 1, and then first increment the second entry here until we exhaust all different possible values, and then we increment the first one. This is a pretty huge vector, so let me try to group it into a vector symbol. You get the idea, this is a very large vector. Indeed, it has n times n components. And this fact that the number of components increases so drastically is indeed the reason why quantum systems can be so complex. Just by composing a few systems with a few states, this is an exponential increase in complexity of these systems, but this is one of the features that we want to exploit exactly in this course, so that we can store a lot of information into just a few quantum systems. Now, to keep things manageable, we will group these vectors here further into subvectors, which we can enumerate in the following way. So we would write chi simply as a grouping of vectors, so little segments of the vector, each with m components. Now what I've written down here suggests that there is a formal way to combine the basis states of two different Hilbert spaces, H1 and H2, into states of another Hilbert space, H3. And even though we will not really need the detailed mathematics of this, I just want to mention that this is known as the tensor product of these states. So this is denoted with the circle and a cross in the middle. And oftentimes we would even omit this symbol for this multiplication here. So this would actually just be another way to multiply two vectors, but different from the scalar product that we have encountered so far, or the combination of products that we encounter when we define an operator in the Dirac notation. So this is our third version of a product, and this is known as the tensor product. But in our context, this will always be very simple, because we simply can interpret this, as I said, as representations of numbers, and we are just enumerating all the possible states of these composed systems. Now, with this, we can of course also introduce a dual state. And here we just have these complex conjugated amplitudes and these states pointing into the opposite direction. And observe that we keep the order of the entries. So this we are not going to interchange. And in terms of vectors, this would just now be a row vector with just complex conjugated entries, but with exactly the same ordering that I introduced above here. But importantly with a complex conjugation. So if we call all of this here as a vector, again as chi, not in Dirac notation, but just as a vector, then this would just simply be chi dagger, just a Hermitian conjugate. And therefore, when we want to work out the scalar product between these states, this is really just the same scalar product that we have encountered before. So if we have two states, maybe a state phi with similar components in here, then phi times chi, the scalar product, would simply be the sum over n and m, phi n m complex conjugate, chi n m. And this you can again write also as phi dagger times chi. So this covers all that we need to say about the states at the moment. This is the complete definition. In these definitions there are some very fascinating features hidden, which we will uncover as soon as we have completed the definitions of the other aspects of these composed systems. So next let's have a look at the observables of these systems. Now we can distinguish basically three different types of observables. Those acting on the first part of the system only, those acting on the second part of the system, and those acting on both parts of the system in a way so that they cannot be associated to an observation of just one part of the system. Now, as always, the action of these operators is specified by telling us what they actually do to states. So let's have a look at what they do to a general state of a form as given above, but I'm now just going to use again the normal symbol psi instead of chi, because we are just now focusing on these states and we just use the ordinary symbol for quantum systems. So now let's first have a look at what an operator for an observable of the first part of our quantum system is going to do to such a state. What I mean by this is that we assume that if we study this system in isolation, there would simply be an observable associated to an operator A. And now we want to see how we can elevate this to an operator or observable of the composed system. So as indicated here, we would give just an index 1, indicating to which part of the system this observable is connected. And then when we act with this on the wave function, we will simply define it in the following way. Namely that we work out what this is going to do if we were just studying the system in isolation. And then we take the product of these states, such as here. Now we can write this even more explicitly if we simply specify the action of this operator on the first system in terms of the matrix elements of this operator in this basis. So if we insert this in here, then we get a triple sum nmk, psi nm, a nk, and then simply the states km. So as I said, we don't really need the tensor product here. We just reduce it immediately to some operation in the Hilbert space just enumerated with all these different combinations. Now this does not quite look like a matrix multiplication at the moment, but we can actually rewrite it very nicely as a matrix multiplication if we make use of this form of grouped subvectors which I introduced before. What we then see is that this result here can be written in the following form. So we take all these matrix elements of the operator that is defined here, all these matrix elements. This is acting on the first part of the system, so all these indices are running from 1 to n. And then we multiply them simply by an identity matrix with m times m dimensions. So each of these elements here are a block of m times m dimensions, and we have exactly n of these in both directions. So this is an n times m times n times m dimensional matrix. So we have n times m entries in both directions. So this is a square matrix of exactly the correct dimensions to act on a vector in the Hilbert space of our composed quantum system. Now we should ask, how does this look like when we have an observable associated to the second system? Again, we would have exactly the same type of definition, but just on states acting on the second system. So there would be an observable that's already defined if we would just study the second part of our quantum system in isolation, not knowing that there is a first part, for instance. And then we will have an associated observable A2, and this is acting on this exactly in the analogous way. Such as this. And then we can again insert these definitions, but now with indices m. Just as before. Now this suspiciously looks a little bit like a matrix multiplication. And the reason for is that it actually looks a little bit simpler even than what I have written down here. If you write this in terms of a matrix multiplication on this stage with the same grouping of subvectors as before, such as this, then this will just be a matrix with the matrix A given on the diagonals. Now, as we now assume that this is a matrix of an observable of the second quantum system, this is an m times m matrix. And there will be n of those blocks, just like here, these blocks. And in each of them we populated this just along the diagonal with this m times m matrix A. So this even looks simpler. So you see that the result is really just multiplying each of these subvectors by the matrix A. Now, what I wanted to do here is to really give you the derivation of these expressions. But what we are going to do in practice is to work with these forms simply because they are the general form. What we just need to adhere to is to work with the states and the amplitudes ordered in the correct way, simply as if the indices associated with the states of the different paths are just like the digits of a number, which is a very natural way to order all of the states. So given that ordering, we have these very specific forms for observables associated to the first and to the second part of the system. Now we can also have observables that are not just an observation on one part on its own, but might sort of extract some collective information of the quantum system. But they can often simply be written as a product of the observables of the first and the second system. So what we have written down here is already enough to then generate more complicated objects simply by looking at products of these different operators for the different paths and then maybe looking at sums of such products. So this one is already covered simply by doing products. Now what we can check immediately with these forms is that any observable of the first quantum system commutes with an observable of the second quantum system. And this is essentially because these identity matrices here commute with any observable that you encounter here. And I here specify that this could be even a totally different observable, even if the two systems are sort of alike and have the same dimensions. It could be a completely different observable as long as it is of the other quantum system. Then these two always commute. So these are always simultaneous observables. And this is really what we should expect because these observables are really tied to one part of the quantum system, which might already exist in isolation before we even bring it into contact with another quantum system. Okay, so now let us turn to dynamics, and on the level of general definitions, this is actually very simple. We need the Hamiltonian, which is the observable for energy of the composed quantum system. And in essence, we just want to say that this can be often broken down into three pieces, namely energies associated to the two different parts individually, which are just of the form of operators as I had specified before in these block forms, and then terms which represent energy that is sort of shared or generated by the interaction of the two different parts, and indeed these we call interactions. So here we have interactions, and here we simply have the so-called non-interacting terms. And this is really all that there is to it. At the end, the time evolution of the state in this composed quantum system is still simply generated by the Hamiltonian, which in principle again can also depend on time. Now the dynamics will of course be very important for us because it will represent the manipulation of information, say in a computation, and we will then nicely exploit that we can break it down into operations that work on individual parts of a quantum system and some very well defined operations that involve interactions between the different parts. Similarly, when it comes to measurements, we don't really need to do any further adaptations because the general measurement postulates simply hold also in this case. Because we have already defined the observables, we can still work out all the eigenstates and eigenvalues. And looking at these block forms of these matrices, this is very simple if we think about observations of just a single part of the quantum system. But we can now start to ask interesting questions. For instance, what are the eigenstates of one of these observables of just one part of the system? And this is indeed quite simple. For instance, if we look at an observable which has eigenvalues A and associated eigenstates just labeled by the eigenvalues, and then we want to work out what the corresponding eigenstates and eigenvalues are for these operators then acting on one part of the system. If this represents an observable acting on the first part of the system, then we can simply write all the eigenstates in this composed situation as the product of this eigenstate here and a completely arbitrary state of the second system. Because according to our rule, this will simply give us exactly this result here. Our general definition told us to act on this state just with this operator. So we just extract this value, this eigenvalue here, and we can just pull it to the front. So this is indeed still an eigenstate. And if we do the same for an observable for the second part of the system, then we can simply write it like this. So the eigenstates are just of this form here, again with the same eigenvalues. So this is completely symmetric as it should be, because these labels, what we call the first and the second part, is of course just our own choice. So in the mathematical description there cannot be anything that really gives a different status to the two different parts. The only place where we give a slightly different status is in the ordering of the entries in this very long vector. So we take a particular ordering where we just increment one of the elements of the indices first and then the other one. And that's the only reason why we sometimes see slight differences in the mathematical expressions, but physically the two parts are really on equal footing. And mathematically indeed too, if you just take this specific choice of the ordering of all the coefficients into account. Now with this we know that the measurement outcomes with these sort of observations are just the same as before, associated with these eigenvalues here. So nothing changes by enlarging the system. If we still just make observations on some part, we will just get the same outcomes in principle. And we can also work out the probabilities. And we will have the same drastic effect on measurements on the quantum system, namely that it forces the system into one of these eigenstates. And as we see here, this drastic effect is then mostly felt by the part of the system that we are measuring. Or at least it looks like this. A lot will depend on the nature of the states of the corresponding counterpart in the other part of the system. Indeed, this poses two very interesting and natural questions. How do the different parts of a quantum system influence each other? And how can we describe a quantum system when it is made out of several parts, but we maybe have only access to some of them? And in particular, what sort of information can we then still extract about this quantum system? Now, the answer to this is twofold. If we make observations on just a part of a quantum system, then we can still completely describe this by introducing a more general notion of a quantum state, and this is known as the density matrix. And by inspecting when this density matrix gives us a really generalization of our normal notion of a quantum state, we uncover a new phenomenon, and this is known as entanglement. And along with the superposition principle, entanglement is indeed the second key resource for quantum information processing. So what we are going to do next is to introduce this density matrix, and then we are going to discuss entanglement. First, however, we are going to have a look at a composed quantum system made out of two two-level systems.